Good morning. Myself Sheikh Abdul Qayyum. Today I am going to discuss sorry. Today I am going to discuss about solid mechanics, one part of solid mechanics, that is one module you already have, that is analysis of truss, and I will discuss a few basic things about analysis of truss today. I have already dealt with few chapters already in the class. Now today we will start analysis of truss. Now, before going to the analysis of trust part, first of all, we will discuss about what a trust actually is. Trust is actually a framework. A trust is actually a framework that is composed of members joined at their ends to form a rigid structure. So just look at this one. This is one member. This is another member. This is one member. This is one member. This is one member, this is one member, and like this one there are lots of member and which are joined together at their ends. You can see this member, this member, this member, this member are joined together at their ends, and after the joint has been done, they after they are joined together, and ultimately they are making it a rigid structure, so which you cannot deform very easily. And this is actually this kind of structure, those who are joined together, when members are joined together at their ends to form a rigid structure, they are generally called truss structure. Now these joints is basically welded, riveted, bolted or pinned joint. So you cannot provide a fixed joint at any section of a truss. All the joints should be pinned joint. Ideally, idealization of these joints is pinned joint, but in practical implementation, we generally provide welded, riveted, bolted, or pinned joint, and which is idealized at as hinged or pinned joint. Now, this is one truss. If we take it out at this side, we will see that this truss is within one particular plane, and that's when the truss lie in a single plane, we call that as plane truss. When members, all the members of the truss lie in one single particular plane, then we call that as plane truss. Now, what are the basic elements of plane truss? Basic elements of plane truss is triangle, as you already have seen that one member, another member, and three members in this particular figure, that there are three members, they are joined together at their ends, and ultimately they are forming a rigid structure, and which leads to a formation of truss. And if you can see in this structure as well, you can see the intermediate shape of the joints, in between the joints, the shape uh, they are formed with is just triangular shape. There is lots of triangular shape. It looks like some interconnecting triangles. So truss is made of some interconnecting triangles, and that's why the basic elements of a plant truss is triangle. It is assumed in some special cases there may not be triangular shape in one particular section, but in most of the section you can found the triangular shape as the basic element. So in truss structure, structures are built from basic triangles. And why do we provide triangles actually? One more benefit of the triangular structure is that, uh, suppose this is one triangle, and if this is not a triangle, clear. So while we are applying force at these particular points, suppose we are applying force at this particular section, so what will happen actually, this cannot deform in this direction. Can it deform? because in order to deform in this direction, what actually uh, the structure will undergo, if this particular joint comes in this position, then what will happen? Actually, the length of the member will increase. The length of this member will increase. So for the deformation in truss structure, the main basic criteria is that the uh, length of the one particular member will either increase or decrease. In this case, the length of the member will decrease. In this case, the member of the length of the member will decrease. And as you can know, if you just take one steel section, and if you try to deform the body in the axial direction, it is a very tough job to do this one, because the steel structure are generally very show a greater strength while you are trying to pull it apart, or you're trying to uh, provide some compression, some sorts of compression. So it is very tough to deform the one particular member axially. So that's why the triangular shape gives a very considerable contribution while the strength comes in play. Whereas if we compare the same thing, if we apply the same amount of force in the same angle, what will happen if in this structure, the structure will easily deform, because these are all pin joint. So it is very easy for this structure to deform in the while the applied force are same. As you can see, it is very easy. It can easily sway in this direction. So basically, the triangular shape is the most rigid structure so far the structural configuration is concerned. But if you provide one member like this in this particular, like, let's take some different colors. Now, if we give one member in this direction, what will happen? Now, can you deform it easily? No, you can't, because if you try to deform, you have to go through this member should, you have to reduce the length of this particular member, and that is a very tough job, because you have to this member is under compression. If you try to make this pull this section in this side, this part will be under compression, and in order to sway in the right direction, these members must be shortened, and which is very tough in comparison to the previous case where there was no internal joint in between this B and C link. Now, determination of the member forces. What we will actually do, we will determine the member forces. Let me remove all this first. In analysis of truss part, actually what we do, we actually determine the member forces. What are the member forces? We actually do this calculation. That is the basics of this particular module. So before going to that part, first of all, there is certain assumptions. So for the particular truss structure, so what are those assumptions in order to, with respect to which we can say whether the structure is truss structure or frame structure or different kinds of structure? That is, so there are some certain assumptions based on which we determine whether that particular structure is truss structure or not a truss structure. So what are those assumptions? So first assumptions that all members are two force members. Like, this is one member, and this is suppose this is another member. So all the members should be two force member. Why there will be only two force? That is, two force member means there will be either tension or compression. There will be no other forces acting within this member. This member will be subjected to only two kind of forces, tensile forces or compressive forces. But why these members are undergoing only tensile or compressive forces? While in the analysis of beam part, you already have seen the beam undergo tension, may undergo tension, may undergo compression, may undergo bending as well. So in this case, actually the bending there is no contribution of bending moment, actually, because as you have seen that all the joint of the truss structure is pinned joint. I have already discussed about this. The joint are pinned joint, and when there is pinned joint, we are actually allowing rotation. So when we are allowing rotation, that is no moment will be developed at any particular joint. So when moment will not be developed, so there will be no resisting moment, so no moment will develop. And actually what will happen, if no moment developed at this point, then there will be only forces, that is either vertical forces or horizontal forces, and ultimately their component will be there. Clear? So when there is vertical forces or some sorts of horizontal forces, we can figure out what are the uh, effect of those two vertical and compressive forces. And if you analyze that, if you uh, you can see that the forces will go through the axis of that particular member. All the forces will go through the resultant of those vertical and horizontal forces will go through the axis of the member. Why? Because actually what happened, suppose if there is one forces in this direction, another force is in, sorry, another force is there in this direction, suppose. So what happened if the resultant go in this direction? Suppose, let me assume that resultant is going in this direction. What will happen? In order to maintain equilibrium, in order to maintain equilibrium, if this is resultant, in order to, and the direction is this, if this is resultant and direction is this, so what will happen? In order to maintain equilibrium, there should be a equal and opposite forces in the exact opposite direction that of R. So there must be some equal and opposite forces. And if you apply this kind of forces, it will undergo bending. If there is some restraint, if there is some restriction, it will undergo bending. But so far our assumptions is concerned, our joint is pinned joint, so there will be no bending consideration. There will be no bending moment happening within this particular member. So if there is no bending moment, then actually, as I have already discussed, the truss structure member actually take loads axially. So if the member takes load axially, then the resultant must be in this axial direction. And if this resultant is in this axial direction, then the opposite force must be in this direction. So ultimately, the our system will undergo tension or compression. So that's why we call our truss structure as two force structure. Truss members as two force member. Clear? And one more important thing, while truss structure is considered, weight of the member is very small in compared with the force it supports. That is, suppose if you consider a whole structure, a whole truss, we consider the members, the weight of the members are very little. So there will be no such effect of the dead load of these members. So in any case, if the weight is much, we can consider that weight or apply, we can apply that weight, we can consider that weight by applying force at the joints itself, but not in between any member. Clear? So when we consider the truss structure, we have to consider that the weight of the member is very small. And if in any case the weight is not so small, we have to consider the weight and apply those forces due to the dead load or weight of the member at the joints only, and not in between any part. You cannot apply any forces in between any members. So you have to apply load only at the joints. no effects of bending members even if weight is considered. So even if we are considering weight, we cannot consider the bending effect. Now external forces are applied at the pinned pin connection. So when we are applying in the dead load, I have already told you that we will apply that forces at the joint itself and not in any in between any members. At the same time, while we are going to apply some external forces, we have to consider that the external forces are applied at the joint or itself and not in between any parts of the member. So actually, basically in truss structure, loads are applied at the joints only. If we summarize that, then the loads of the members are applied at the joints only. Clear? And welded or riveted connections we make provide, and pin joint if the members, and when we can say one particular joint is pin joint if the member center lines are concurrent at the joint. So this is one member, this is one member, this is one member, and this is the another member. So as you can see, the center line of all these member 1, member 2, member 3, member 4, they all are coming in one particular point. That is, they are the center line of those member are concurrent. In that case, we can say that this particular joint is a pin joint. Now there are some common practices in large trusses. What are those common practices? We provide roller or rocker at one end. This is roller or rocker. So we provide roller support or rocker support at one end. Once at another support, we generally provide hinged joint. Clear? We provide hinge joint at one support and roller or rocker support at the another point. This is one of the basic common practices. Then why actually we do this? Suppose due to this load L, if the whole structure undergo a little bit deformation, then, and in case of truss structure, as we have already discussed, the deformation takes place in the axial direction. So all these members deform axially. So if they deform axially, so either the truss will go from this point or the truss will come to this point. So they will, if they deform, they will either go this in this direction or they will go in this direction. So in order to allow the whole structure to deform, we have to provide rocker or roller at one particular joint, or one particular support. So that's why there is a basic uh, practice to provide roller or rocker support at one end. Otherwise, if you don't provide a roller support, what will happen? Actually, suppose, let me assume that this is not a roller support and this is a hinged support. What will happen? It will ultimately become an indeterminate structure. So what actually indeterminate structure, statically indeterminate structure, we will discuss it after in the next lecture. So as for the time being, you just assume that if we provide hinge support at both the ends, then it will become statically indeterminate. Now what is static? Okay, we will discuss static indeterminacy and indeterminacy today itself. What is static indeterminacy and what is statically determinate structure? Actually, we already have seen in the analysis of beam, in the engineering mechanics part, you have already seen that while analyzing a beam, it is very important to first understand whether the beam is statically determinate or statically indeterminate. So in that case, we have already seen the statically determinate structures are those where the number of unknowns are very equal to the number of available equilibrium equations. So when the number of unknowns is equal to number of available equilibrium equations, so that kind of structure we may call that statically determinate structure. But in case when the number of unknowns is more than the number of available equilibrium equations, that kind of structures we call statically indeterminate. So now in the case of Truss, what actually we have to determine whether that particular structure is statically determinate or statically indeterminate. So how can we analyze that? So as you can see that all the members are two force member. I have already discussed. So if we take out one particular joint, first of all, let me uh, just determine what are the unknowns, how many unknowns are there in this particular. Let's go through take let's make you understand through this particular example. So first of all, we have to determine what are the unknowns which we need to know. Unknown, what are the unknown means, what are the unknown reactions. I am not talking about the unknown member forces first of all. So what are the how many unknown reactions are there? You have already learned how to determine the unknown reactions. So there is one vertical reactions at point A. There will be, because this at this particular point the vertical, uh, it is restricted vertically. At the same time it is restricted horizontally as well. So there will be two reaction, one in the vertical direction and another in the horizontal direction. So in this particular point there will be total two number of unknown reaction forces at point D. This is another support. So as we have provided a roller or rocker support, so roller or rocker support generally provide, allow deformation in the horizontal direction. So as it is allowing deformation in the horizontal direction, there will be no such reaction in the horizontal direction. So it is only restricting the structure to deform in vertical direction. So there will be only vertical reaction because it is restricting this structure to deform only vertically. So there will be one vertical reaction at this particular point. So in the whole structure there is one, two, and three unknown reaction, three unknown reaction in the whole structure. So if we take the unknown reaction, number of unknown reaction, if we assume as R, then how many unknown reactions are there? There are three unknown reactions. And in the analysis of Truss, what we actually determine, we determine the member forces. What are the member forces due to these loads? What are the uh, forces that are introducing within the members? What is the forces that or each member is undergoing? What is the stress each member is undergoing? So in order to find out that, we need to know what is the member forces in each of this member. So in order to know the member forces, as in this particular member there will be one member forces, at this particular member there will be another member forces. So how many members are there in this structure? One, two, three, four, five, six, seven, 8, 9. So there are nine members, and at each member there will be one unknown member forces. So if the number of member, if we denote is at as M, then uh, total unknown member forces will be M. So if we combine these two, that unknown member forces and unknown reaction, that then we will get that total unknown. What are the total unknowns within the structure? That is M plus R. That is M is the number of member. So M number of member forces, that is unknown to us, and R number of reaction forces, that is also unknown to us. So total unknown within the structure is M plus R. This is the total unknown. This is the total unknown. This is the total unknown. M plus R equal M plus R is the total number of unknowns. And now we need to know. We now first we have determined what are the how many numbers of unknown are there within the structure. Now, how many equations of equilibrium do we have to solve this particular structure? So, as you can see, suppose let's take one particular joint. If we take out joint A, take out joint A, there is one reaction, horizontal reaction, there is one vertical reaction. There will be one member forces acting. This is force, member force AB, and one member forces will be acting in this direction, that is member force AF. Clear? So this is one member force, this is one member force. This is unknown reaction, this is unknown reaction. We have just drawn the free body diagram of this particular. We have just drawn the free body diagram of joint A. This is free body diagram of joint A, and you know already how to solve this kind of structure. This kind of problems. You know how to solve this kind of problems. To solve this kind of problems, we apply the equilibrium equations. What are the equilibrium equations? Sum of fx equals to 0, sum of fy equals to 0. These are the two equilibrium equation. We all have another equilibrium equation, sum of moment equals to 0, but uh, the sum of moment equals to 0 do not have any contribution in this particular cases, because when we are considering one particular joint, and you can see that all the forces are concurrent, that is all the forces are going through this one single point. So if we suppose take moment about this point, then what will be the moment ultimately? Zero, because moment is the uh, multiplication of force into perpendicular distance. So if the perpendicular distance is 0, why the perpendicular distance is 0? Because all the forces are passing through this particular point. So perpendicular distance of this point from all those forces will be ultimately 0. So if the perpendicular distance is 0, ultimately our moment will be 0. So there will be no contribution of the sum of moment equals to 0. You will get nothing out of that. So in the in case of truss structure, while we are analyzing, we have only two available equations at one single joint, that is sum of fx equals to 0 and sum of fy equals to 0. Now again, if we take out joint B, again we will get another two equations, sum of fx equals to 0, sum of fy equals to 0. If we take joint F, again we will get another two equilibrium equations, sum of fx equals to 0 and sum of fy equals to 0. Just after applying sum of fx equals to 0 and fy equals to 0, we will get another two equilibrium equations. So for n number of joints, we will get n into 2, that is 2 into n number of equilibrium equations. So if the number of joint is j, if we denote the number of joint as j, so how many joint is there? 1, 2, 3, 4, 5, 6. So there are 6 joints. So what are how many equilibrium equations will we get? We will get 6 into 2, that is 12 equilibrium equations we will get. And how many unknowns were there? 9 member forces and 3 unknown reactions. So 9 plus 3, 9 and 12. So there is 12 equilibrium equations we have, 12 unknown forces we have, and 6 into 2, 12 equilibrium equations also we have. Just put the value of m plus r. M is here, number of member is 9, number of member is 9, number of reaction is unknown reaction is 3, and number of 2 into number of joint is 6. So in this structure, you can see 9 plus 3 is 12, 6 into 2 is 12. So it will be equal. So if the number of unknowns is equal to number of available equilibrium equations, the structure is statically determinate structure. Statically determinate structure. If the number of unknown is more than number of available equilibrium equations, then we can call that structure as statically indeterminate structure. Clear? So basically you need to understand this. We need to remember this one: m plus r equals to 2j when statically determinate structure, and if m plus r is greater than 2j, then it will be statically indeterminate structure. Clear? So for this we will stop here today, and next day we will discuss after this. Thank you.